Okay, welcome back everyone. Hello. Winter is back, as we can see. Okay, in more ways than one. Did anyone watch Game of Thrones on Monday? Did you like the ending? No spoilers? Well, what happened was... I think those two are my favourite characters at the end of their first episode. You know what I'm talking about. All right. Today we're going to put pretty much everything together that we've done over the last week and a half. So everything you learned from what it means to make something binary, turn information into a digital form, all this binary algebra, these logic gates, all this kind of stuff, we're going to put it all together. And then tomorrow we're going to go through some real design examples of the stuff that we're looking at today. So today we're going to put it all together and show you what you can do. And then tomorrow's more like an exercise class where we'll have a few case studies and examples and we'll apply what we've done today to that. Okay, so this is entitled Synthesis of Logic Circuits. What does synthesis mean? If I synthesize something, what does that mean? I artificially create. I like that. That's pretty good. So we artificially create logic circuits. So we create logic circuits from a specification. Okay, so at the end of this lecture, you will be able to synthesize logic circuits from truth tables. So we've done a bit of work on truth tables the last couple of lectures. Use those to synthesize some efficient logic circuits. So we'll show you how you can synthesize any old logic circuit using what we call sum of products and products of sum representation, SOP and POS. And I'll show you how to synthesize a logic circuit using only NAND gates. Why is that useful? Because you can buy arrays of NAND gates and make connections between them to rapidly create a logic circuit. And finally, a really big important one is to make this efficient. So I'll show you how to simplify any logic circuit into its simplest possible implementation using a method called Karnaugh Maps, or K-Maps for short. Okay? And this will minimize the number of logic gates that you require to implement any function. Okay, so far we've looked at the truth tables. We've made truth tables from functions and logic circuits. Is there a systematic way to produce a logic circuit from any truth table? And of course there is, otherwise this wouldn't be a topic. And I'm about to show you how. So, first key thing that you need to remember is the sum of products method, SOP, sum of products. So let's say we're given this arbitrary truth table. Now this truth table doesn't necessarily represent any particular function. It just represents a set of inputs mapping to a set of outputs. So a set of binary inputs corresponding to high and low voltages. And on the output, we want an output of a high or low voltage or a 0 or 1. Okay, so from this truth table, you can see that the highlighted entries in orange are the rows in which the function is a 1. Now, this is important because what we want is for our circuit to only output a 1 for certain combinations of inputs A, B, and C, right? That's the objective here. The objective is for a certain combination of inputs A, B, and C, we want the circuit to output F equals 1 for only very specific sets of A, B, and C. And those sets here are A equals 0, B equals 0, C equals 1, A equals 0, B equals 0, C equals 1, A equals 1, B equals 0, C equals 0, and A equals 1, B equals 1, and C equals 0. Any other inputs by this truth table, we're saying we want an output of 0. Okay, so how do we do this? Well, the easiest way to do this is to use a gate which detects when certain inputs are exactly correct. And it turns out that that gate is an AND gate. Okay, so we can use a number of AND gates. We can use one AND gate per row of inputs, okay, to detect. So here we can detect when a certain combination of inputs has been satisfied. Okay? So over here, this first row detects when the input A is equal to 0, B is equal to 0, and C is equal to 0. And how does it do that? Well, what it actually is detecting is we put in the inverted input of A. So when A equals 0, what will this be? What will A prime be? 1. And when B equals 0, B prime will be, and when C equals 0, C prime will be, right. So if I put in this input into this AND gate, it will detect this first row, row 0. So we can call that row 0, right? And so on for the other gates. So if we look at this, say this fourth one, we have, if I put in A equals 1 into this input A, then that will be a 1, which goes into the AND gate, right? If I put in B equals 1, then you'll get a 1 on the input. If I put in C equals 0, then C prime becomes 1. So you'll notice that all of these gates will have inputs of 1 if and only if that particular row has the exact combination of inputs required. Does that make sense? So each of these AND gates is detecting a specific row, and how we determine which row we're detecting, how we determine which row we're detecting is given by the input that we give on that row. So it might be the variable, or it might be the inverse of the variable. And if we're giving it the inverse, we denote this by putting in a prime or an inversion on it. Okay, so each of these terms will give us, well, each of these AND gates will give us a particular term. So this first AND gate gives us, well, it'll be A prime and B prime and C prime, and so on for the other gates. And it turns out that each of these terms is called a minterm. So this is definition here. Okay, these are called minterms. A minterm is a term which corresponds to one row of the truth table. So this row is A prime, B prime, C prime, and in binary, that would be 0, 0, 0. So we call that row 0, or alternatively, you can call that minterm 0. Okay? Minterm 0. This would be minterm what? Minterm 1, yes? What would this be? Minterm 4, because we've got this row corresponding to this one. So this would be minterm 4, and this would be minterm 6, yes? Okay, row 6, 1, 1, 0 is 6 in binary, so that corresponds to minterm 6. Then we take all of these and we chuck them all into an OR gate. Take the outputs of these AND gates, put them into an OR gate, and what we get out is, we get out D equals, now it's the ORing together of all of these terms. So this is A prime, B prime, C, plus A, B prime, C prime, plus A, B, C prime. Okay, so that's, now this logic function here, completely implements the truth table that we've got on the left-hand side here. So if I give you this truth table, this logic function will only give a 1 whenever the exact rows of the highlighted rows give a 1 on the output F. So this is a long way to write it. Another way you could write this is that this is the sum of minterms number 0, 1, 4, and 6. Okay, and you can write that in shorthand by using a capital summation of min terms 0, 1, 4, 6. Okay, they're just some alternative ways to write it. But generally, when we're asking for the sum of products term, it's going to be what's written here. Now, why is it called sum of products? Because, as the imaginative engineering name suggests, it's a sum, like we've got all these sums, of a number of product terms. These are all products. Okay, so it's a sum of products. Okay, so in this case, how many AND gates do we need? You need as many AND gates as you have min terms. Right? So if alternatively this was a 1, this was a 1, and this was a 1, how many AND gates would I need in that case? 7, right? Because if I had 7 1s in the truth table, then I would need 7 AND gates, 1 to detect each row of my truth table. Okay, and then incidentally, this is the sum of products circuit that implements this truth table. Okay, so if I build this circuit, I get a number of AND gates, I put an OR gate after it, and I connect them all up as shown with inverters on the specific inputs, depending on the row that I need. Then the output of this circuit will be 1 if and only if I have row 0, 1, 4, or 6. Okay, that's the sum of products. Now, that's all well and good, but if I had this truth table here, I would need if I had the truth table where I've got 7 1s in it, that means I would need 7 AND gates. What if I just look at the rows of zeros? Does that make a difference? Well, you can do that. And if you do that, the method that you come up with to produce logic is called the product of sums method. So it's sort of the opposite of the sum of products, POS-SOP. Okay, and in this case, what we do is we identify all the rows which are 0 in the truth table. So from that last example, these rows are 0. And similarly, these are called max terms. Okay? Max terms are rows which are 0. And what we're saying here, essentially, is that this truth table is a 1 when we do not have row 2. So we don't have row 2. We don't have row 2, and we don't have row 3, and we don't have row 5, and we don't have row 7. That's what this logic here is saying in the red. Okay, so you've got, it's not A prime, B, C prime is what we're saying for this row. And we've got not A prime, B, C, and not A, B prime, C, and not A, B, C prime. Now you've noticed you've got all these nots here over a term which has 3 variables in it. What can we do to these kinds of terms that we learned yesterday or Monday? What law can we use to expand that out? De Morgan's theorem. Great, well done. So if you use De Morgan's theorem on this, then this becomes A plus B prime plus C, and so on. So this one becomes A plus B prime plus C prime, etc. And then if I take these and I implement the logic that I was just saying, then you get a number of rows, you get a number of detectors here which detect all the zeros. And these are OR gates. So this OR gate detects A, B prime, C. This OR gate detects A, B prime, C prime, and so on. And you put them all into an AND gate, and this now implements a function exactly the same as what we have in this sum of products method. Okay, so this is an alternative way to construct this. Now this is called, you can say these are the product of the max terms, max term 2, max term 3, max term 6, and max term 7. So you could say 2, 3, 6, 7. Okay, so this is the opposite of your sum of products method. But it works equally well. But you'll see soon enough why well, we'll see at the end of the lecture why we often like to use sum of products instead of product of sums. Okay, so there's a reason for it. But both of these will give you the same answer, which both implement these truth tables. Okay, so in summary, what this says in the sum of products method, this is the logic you would need to remember. The output is high when the inputs are row whatever, or row whatever, or row whatever, or row whatever. So it's a sum of a product. In the product of sums method, we are selecting rows of 0. The output is high when the inputs are not row 2 and not row 3 and not row 5 and not row 7. That's for this particular table. Okay. Do we have an example? Yes. All right. Here is an example for you to try. Have at it. Oh, I see the melts symbols. We've got a whole load of symbols in melts which are messed up. But just use the A, B, and C you see from the slide. So have a go at this. You may need to rub your eyes because reading the primes or the A prime, B prime, C prime, etc. may get confusing. And if you don't know, then just say you don't know. That's fine. So remember, the sum of products is saying the output is row something and, or row something, or row something, or row something.
Inverting these symbols in this SOP, I just did not get. Why are you doing a complementary?
Yep, so if you come here, so so what you're saying is if you have something like A prime, B prime, C prime, why am I doing that?
Yeah.
Because this will give a 1 if and only if what?
0.
A is a 0,
Yeah.
B is a 0, and C is a 0. Because if any of these are a 1, then it turns this input into a 0,
this
right?
is AND gate, yeah?
That's an AND gate, yeah?
AND gate, not AND.
That's right. It's not an AND,
Yeah.
it's an AND gate, yeah. So if I have this on the inputs, then it will only give a 1 when I have this row where A is 0, B is 0.
Oh, had it been AND gate, then we should have put ABC.
That's right.
But this is an AND gate.
This is an AND gate, that's
so
right.
That's why we are keeping the inverse.
That's right.
Oh,
to detect a specific row.
Thank you.
That's all right. How are we going? All right. Looks like people are pretty set. Okay. 5, 4, 3, 2, 1. Any last minute changes in answers? All right. Let's have a look. Here we go. All right, so pretty clearly people think it's C. Okay, and I apologize for all these crazy symbols on the Zelt system. It obviously has taken the prime and given percent %U2019 instead of a prime. Okay. Okay, so yes, correct. It is in fact C. Well done. So glad to see you all understand how these come from the truth table, right? These correspond. Very good. Well done. Okay, great. Okay, so why do we want to use the sum of product circuit? Well, here's why, because any sum of product circuit can be converted into a circuit which only uses NAND gates really, really easily. So say I'm given any sum of product circuit, so this is a sum of product circuit, AB plus CD. Well, all I have to do is replace each one of these gates with a NAND gate. All right, so this is replaced with a NAND, that's replaced with a NAND, and that's replaced with a NAND. Okay, that's all you have to do to convert any sum of products circuit into a NAND gate implementation. Okay, so you've gone through, you've designed your circuit to do something in particular. It might be you've designed it to add two numbers together. You've got a lot of AND gates and OR gates. Well, you want to now implement this in a chip. You just need to program on the chip where the connections are between all these NAND gates, because the chip that you've bought only has NAND gates on it. Okay, so that's why you would want to do this. And there's a similar result for NOR gates. Can anyone guess how you would do it from NOR gates? So the way that works is you use the product of sums method, and you replace everything by NOR gates. Okay, and that would allow you to implement that function using only NOR gates. And both of these crop up because of the use of De Morgan's theorem. Okay, and we went through an example like this when we looked at De Morgan's theorem, and that's how it ties back into what we're doing here. Okay, so now you can design any circuit. I give you any truth table that doesn't have 50,000 variables in it, and you can, by hand, very quickly look at that truth table and come up with a circuit, either a sum of product circuit or a product of sum circuit. Now, incidentally, when might it be better to use a sum of product circuit versus a product of sum circuit? Depending on the truth table. What do you think? Yep, so when there are less zeros on the truth table than ones on the truth table, you would use what? Product of sums. And if there are less ones on the truth table, then you would use sum of products if you wanted to use less gates. Right? Does that make sense? Because product of sums, you need a gate per 0 row, and sum of products, you need a gate per 1 row. So whichever is less is the one you would like to use. Okay. So now you've been able to design a circuit, but you're running under a cost constraint. You can't buy too many components, and what you need to do is use as few logic gates as humanly possible. So the sum of products and products of sum have given us a systematic method using min terms or max terms to give you a circuit, but it's not necessarily, and often is not, the most efficient and uses the fewest logic gates. Here's the standard way how we minimize the number of gates used after we've come up with a sum of products or products of sums implementation. Okay? And this is an easy graphical method, and it's graphical because we use pictures, and you'll see very shortly that using those pictures allows us to really quickly minimize a set of logic. Okay, so just before we get into that, I just want to introduce another set of outputs that are possible. Okay, so right now all we've talked about is for a particular circuit, its output is a 0 or a 1. But in fact, when you design a circuit, sometimes some of these inputs may never occur. Okay? So let's say you design a circuit that takes in 10 digits, but you're using 4 bits, right? So 10 decimal digits in binary, but you're using 4 bits, which means you actually have 16 different combinations of ones and zeros, right? So that means you've got 6 left over. And in that example, for those 6 left over, you might say, I don't care what the output of that input combination is. And in that case, I'm allowed to put an X in there, which is the standard industry symbol, meaning I don't care what the output is. If the output's a 0, that's fine. If the output's a 1, that's fine, because I'm reasonably confident that those inputs will never occur because I've designed my circuit to be so. That actually helps us because if I don't care which, if this is a 0 or a 1, this will allow us to, this can allow us to get rid of a number of gates in our implementation of this circuit. Okay, so how does that do this? So let's take this table and let's look at the min terms. Okay, so here are the definite min terms, the rows which are 1. Okay, min term 2 and min term 7. So they're over here, 2 and 7. And min term 2 is A prime, B, C prime, and min term 7 is A, B, C. Now if I say, okay, that is my implementation for F, you would be correct. That is the sum of products implementation. How many inputs does this have? Well, this requires 2 gates, each with 3 inputs, right? And an OR gate to put them together. That's fine. Now, in fact, how are these constructed? Well, often this 3-input AND gate might be constructed as 2 2-input AND gates, right? We saw that previously, and that all might be what's inside that box. So in actual fact, the more inputs you have to a particular gate, if you will, still increases the amount of logic that you require. So it's best if we can minimize the number of inputs as well as the number of individual gates between stages. And that's where these don't cares come in. Okay, so I've got 2 red rows here, which are don't cares. So this don't care over here, 101, is represented by this term, this min term, and this 110 is represented by this min term. How does this help us? Well, it turns out that if I have these 2 min terms, I can do a little bit of algebraic simplification. So this is where our algebra comes in, that we learnt. So you've got A, B, C, or A, B prime C. And if we factorize that out, you can see that if I take these 2, factorize our AC, then in brackets we have B plus B bar, which is equal to 1, as you can see. And so by assuming that this don't care is an output of 1, it could be a 0 or a 1, we don't care, then if we assume it's a 1, we can minimize this ABC term, and take this ABC term, and we can actually get rid of B out away from this term. So you've actually saved an input. So by saving an input, you're reducing the cost and you're reducing the space required to implement this function. Similarly, you could use, if you don't have to use this B plus B prime, you could use this other term here. You've got ABC plus ABC prime, and in that case, this would minimize to AB, and then you'd have C plus C prime in brackets, which comes out to 1, and this comes out to AB. Okay, so by using the don't cares, it's allowed us to use only a 2-input AND gate instead of a necessary 3-input AND gate for min term 7. Okay, so that's really the principle behind what I'm going to show you now next, which is you can group a number of terms together using Boolean algebra and reduce the number of gates, well, the number of inputs required into particular gates. And in some ways, and in fact, you can get rid of a whole load of gates as well. Okay, now what is this magical method? This magical method is called a Karnaugh map, or K-map for short. Okay. What we do is we need to draw a little grid, and in that grid we need the number of terms in the grid which is the same as number of rows in the truth table. So here we've got 8 rows, and over here we've got 8 cells. Right, 8 boxes. Next, we enumerate each row and column. So for each row and column, we give it a designation. So over here, for the rows, I've just decided to say these represent the variables A, B. And this first row represents A equals 0, B equals 0. This second row represents A equals 0, B equals 1. This third row represents A equals 1 and B equals 1. And this fourth row represents A equals 1, B equals 0. Is that clear? You may notice something strange here between these two rows. Why have I not numbered these in binary order? So normally in binary order I would go 0, 0, 0, 1, 1, 0, 1, 1. Right? But I have not done that. And the reason for that is because we need, in a Karnaugh map, the difference between any two rows to be only one variable. And we covered this a little bit and we called it what? What did we call it? Sorry? Grey code. We called this grey code. That's when we first introduced binary numbers. Okay, so these rows and columns need to be numbered in grey code. Okay, so that means that the difference between any two variables must only be 1 bit. So over here, that's difference. Over here, that's difference. Over here, that's difference. We can't have both bits changing at the same time. If you do that in your Karnaugh map, then your Karnaugh map will be totally wrong, and you can't even use this graphical technique. So in the columns, we just put C equals 0 and 1. And now that we've mapped out, so the first part is to get this right. Second part is now to transfer these things in the truth table, these outputs, into the Karnaugh map. So that first row, A equals 0, B equals 0, C equals 0, would go into this, oops. So this is just emphasizing the importance, because it's in big red font, of putting this in grey code. So this first row of the truth table fits into here. A equals 0, B equals 0, C equals 0. Is that clear? So you just look at what the input is, look at the corresponding input, and put in the output that comes from the truth table. So all we do is we do this for every single row. So you've got 0, 0. What's the next input? 1. So that goes in 0, 1, 0. The next input is 0. The next input is a 0. Where would this go? It goes in the bottom left, okay? So be careful here, because you've got A equals 1, B equals 0, A equals 1, B equals 0, C equals 0. That goes in the bottom left. Okay, what's the next input? Next output from the table that comes after this row? An X, don't care. So what do you do with don't cares? You just put them in the table in the same way. So this little don't care sits in here. And then what's the next input? Next output. Another don't care. So that don't care comes in here. And the final output is a 1. Yes? Okay. Great. So now I've filled in my Karnaugh map. What next? So here's the filled in Karnaugh map. And what do? Well, we start now drawing boxes in the Karnaugh map. Okay? What we need to do is draw the biggest box in the Karnaugh map that covers all the ones in the Karnaugh map. Okay, so here's an example of the biggest boxes. So over here, this 1 is covered by this first box, and you'll notice here that it takes in also this don't care, this X. Okay? You're allowed to group x's with 1s, because x's could be 1s. That's what we're saying. We don't care what the input is, so we assume it's a 1. So what we do is we take this group of 1 and x's and we put a box around it. Now there's a caveat here. Box sizes can only be in powers of 2 in the length and the width of the box. I've got that in another slide. You don't need to write it down. Okay? They can only be in powers of 2. You cannot have box sizes being not in powers of 2. They can't be length and width of 3, 5, 6, or 7. You can't have that. They could be anything else which is in powers of 2. We'll show you lots of examples soon. Now, key thing here is that this box over here is actually independent of the value of A. What do I mean by that? I mean that for the two terms which are enclosed in this box, so this one and this one, if we look at their inputs are both 1 for B and they're both 0 for C. Okay, so if I look at everything in this box here, and I look at the inputs which create the outputs in this box, they both have B equals 1 and C equals 0 for this box. So then we say this grouping is independent of the value of A. Similarly, if I look at this box down the bottom right, in this case, which variables do not change for these two? So A is equal to 1 and C is equal to 1, okay. And so this grouping is independent of the value of B. So it doesn't matter what the value of B is. All the terms inside this box are part of this box. So what does this mean? Oh, there's another one here that you could use for completeness. You could do this here. You can do that. And this grouping will be independent of C because A equals 1, B equals 1, and C is equal to 0 or 1. So that's fine. Okay. So in this case, we could say that this one was the case where B equals 1, so this was B equals 1, and C equals 0, and this case was A equals 1 and C equals 1. Now what we do is we look at what these values are, and this one translates directly into this term. So B equals 1, C equals 0 translates directly into B, C prime, and over here A equals 1, C equals 1 translates directly into AC. So what I'm saying is that F is now minimized to be F equals BC prime plus AC. And that was different from what we had in the previous section, which was this one. F equals A prime, B prime, C prime, or ABC. So in actual fact, what we've managed to do is we only need 3 2-input gates. So there's a 2-input AND gate, there's another 2-input AND gate, and then this one means there's a 2-input OR gate. So we've actually reduced 2 inputs out of this circuit, which means that we use less cost because you've got less gates, and you use less space on your circuit. Okay, so that's I don't expect you to understand it from that, and that's why we've got a few more examples. Okay, here's another example. Here's a K-map. Here's an arbitrary function, so the function is different from the previous slide. And it's got 5 ones in it this time. So I've taken this truth table and I've put it into this Karnaugh map, and this is what it looks like. We've got lots of ones here. So the procedure now, we need to draw boxes around ones, around all these ones, and we need to make them as big as possible. We need to choose the biggest rectangle that covers all the logic ones. Okay, and under the constraint that the width and the height of the boxes must be powers of 2. So what would be the biggest box that you could put in that covers the most ones here? What would be the length and width? 2 by 2, okay? So 2 by 2 fits the bill because its length and width are both powers of 2, and it covers the most number of ones possible. It covers 4 ones. So here's the note. The rectangle length and width must be powers of 2. So over here, if I draw the biggest grouping of ones, then let's look at what inputs do not change between each of these elements inside the box. So what elements stay the same for all of these terms? A, right? So for each one of these terms, so this is A equals 1 for both of these, and we can see that it doesn't matter what C is. C could be 0 or 1, and it doesn't matter what B is. B could be 0 or 1. So these are independent of C and B, and this is given as A equals 1. So in actual fact, this term represents simply the term A. How is that possible? Well, if you look at the rows in the truth table here, right, these 4 boxes, these 4 rows in the truth table correspond to this. And if you look at these inputs, you've got, if it doesn't matter what these are, right? It doesn't matter what these are. If A is a 1, then the output's a 1. Does that make sense? It doesn't matter what B and C are. As long as A is a 1 for these 4 rows, the output's a 1. So that's why this box represents A. And it's so, the trickery that we're showing here is basically condensing that Boolean algebra that we did before into a graphical method where we circle the box and we find out which variables don't change. And what that's actually doing is a little Boolean algebra sleight of hand without you actually needing to do Boolean algebra. Okay, so now what is the next biggest rectangle that covers the rest of the ones that are not already circled? A 1 by 1? Any other takers? Okay. 1 by 1 is a good guess. But it's not correct because you can actually put a 1 by 2 here. Okay? So that is the biggest rectangle. This is the biggest rectangle that covers off this lone 1 here. Now, the reason we do this is because let's consider what this term would be if I just had 1 square. Then this would be A prime B C prime, right? Because if I just have this 1 square, the only terms that don't change are A equals 0, B equals 1, and C equals 0. However, if I make that bigger, I do a big circle around here, then what term does not change between these two? B equals what? 1, and C equals 0, right? So C equals 0 for both of these terms. So this would now be BC instead of BC prime instead of A prime BC prime. So we've gotten rid of A as well. Can we see that? So that's the trickery here, and that was how this example was constructed. If you've got lone ones and they're not really alone, they're adjacent to other ones, you can always make bigger boxes to cover a particular value of 1. Okay, so in this case, instead of writing 5 minterms, if I use sum of products, I would need to write 5 minterms, 1 for each of these. I can just write f equals b prime, f equals b c prime plus a. Okay, so there's a big saving here. So here you'd need 5 AND gates and an OR gate. Here you need you need 1 AND gate and 1 OR gate. Okay, how about this one? This is a little bit tricky, and it demonstrates another property of the K-map. K-maps are cyclic. So who's played Pac-Man? Who's heard of Pac-Man? Sorry, I don't expect you to have played Pac-Man. Do you know in Pac-Man when you go off one edge of the screen, you can come back out on the other edge of the screen? is called a wraparound effect. Well, K-maps also wrap around. Okay, so over here, these two are actually adjacent to these two. Okay? So when I'm looking for the biggest box of ones, there's actually 4 ones which are connected together. These 2 ones at the bottom and these 2 ones at the top. They're connected. And if I look at that, then what are the variables which don't change? B. And what is the value of B? 0. So this means this is B prime, yes? Okay, because B does not change and B is 0 for these 4 ones. What is the next biggest box I can put in to cover the lone 1? A 1 by 2, very good, 2 by 1. And that is here. And what is the term that is this one? A is 0. And C is what? C equals 0. So this is A prime, C prime. Okay? Is this starting to make sense? So then the function could be f equals A prime, C prime plus B. That would work. Okay. Here's another one. You've got 4 in the... Now, this is tricky. We've got 4 variables now. 4 inputs and 1 output. In this case, you have to make sure that you've got grey code across here and grey code across here, so particularly these 2 terms. Yeah? And in this case, guess what? All these corners are connected. Okay, because these are adjacent and these are adjacent. Okay? So in this case, f equals b prime d prime would work, because if I look at these 4 boxes, then b prime doesn't change and d prime doesn't change. Okay, what about this one? So you've got 4 here. Well, 1 big box. That would work. Over here, now we've got a 4 by 1. That's permissible because the rows and the columns are powers of 2. So in this case, what does this represent? This represents A prime B. So A equals 0 and B equals 1. So this gives us A prime B, because amongst these 4 cells, these variables do not change. Over here, we've got 2 groups of 4. So here, A prime C prime plus AC would work. Okay, so you've got AC here, A prime C prime. Over here, now you've got loads of 1s. Well, you've got 4 1s here and 4 1s in a row. So we're covering off most of these strange cases that might occur. All right, how about here? So you've got 3 rectangles. Now this 1 here cannot be connected to anything else. That's a pity, because he's feeling really lonely, and also it means that our circuits cannot be simplified out of this A prime B prime C prime D. Okay? So note, the smaller the rectangle that you make, the more terms are required to define its position. Okay. This map and this map are exactly the same, except we've got a few don't cares in here. Okay? So we've put a couple of don't cares in here. How does that help us? Well, it turns out that with these don't cares in here, I can make bigger boxes. So these 4 1s are the same, but I can make a box of 4 here, and this little lone 1 actually now has a don't care next to it, which can be used. So you can use a don't care if it helps, but if it doesn't help, like this one over here, you don't need to cover it in your rectangle. Okay. Let's finish here today. I'll finish this off tomorrow and we'll get into some examples. All right, thanks very much.